Welcome to the Cosmology and Jesus podcast. I'm Dr. Jeff Groah. Today we're going to talk about what happened before the Big Bang. To begin our discussion, we'll talk about coordinates placed on spacetime. We usually think about coordinates in space. We have Cartesian coordinates, x, y, and z, that describe positions of points within a three-dimensional volume. For a surface, you have two different directions that you can go. You end up with two coordinates. But they make a grid that allows you to distinguish between points on the surface. Each of those grids has its own directional vector that can be attached at each point. Those vectors are tangent to the surface in the direction of each of those grid lines. In space-time, we have coordinates x, y, z, but also time. So one of those grid patterns will represent a timeline direction. The other one might be a spatial direction. In the Big Bang theory, the universe starts out at a point with the universe expanding. Each of the dark black circles here can be thought of as a cross-section of space at a fixed time. The earliest time is at the vertex at the bottom of this elliptic paraboloid. The space will get bigger and bigger, expanding. Those little circles will have a bigger and bigger radius as time goes by. Time goes up, but the time vector field is in the direction that space is expanding at each point. Looking at that time vector field, as time increases, the spatial cross-section will be a little bit higher. Those time vector fields will still be tangent to the space-time. What about in the other direction? What happens at earlier times? At earlier times, you can see that the spatial cross-section is quite small, and our directional arrows seem to be poking away from each other, away from that center. Diverging vector fields are vector fields where the arrows get further and further apart, whereas a converging vector field has the arrows coming together, converging towards each other. This is an example of a vector field that has infinite divergence at the center point. The vectors cannot be extended back any further than the origin. And that's exactly what is happening at the Big Bang. The time arrows cannot be traced any further back than the time of the Big Bang. That means that time has no meaning before the Big Bang. Even the word before is inappropriate to use, because what does it mean to be before when there is no such notion as time? If t equals 0 is the time of the Big Bang, there are no t values less than 0. Another way to view this is to look at the divergence of the time vector field. Here, the vector d dx mu is one of the coordinate vectors for our space-time. And if I compose that with the Kronecker delta, delta mu 0, what I'll end up with is the time vector field on the left, d dx 0. So in some sense, I can describe the components of the time vector field using this Kronecker delta with the repeated up mu and down mu. We use the Einstein summation convention to sum over all possible values of mu. The Kronecker delta is defined so that if the two indices, mu and nu, are different, it will output 0. You only get 1 if mu equals nu, if the two indices are the same. The covariant divergence is, first of all, symbolized by a subscript with a semicolon, and then mu, the repeated up-down mu, indicating that we're calculating a divergence. The covariant divergence is, by definition, the partial derivative, denoted by the comma on the next expression to the right, plus the Christoffel symbols, gamma, mu, mu, sigma, up against the coordinates of our time vector field, delta, 0, sigma. Note that when I take derivatives of the Kronecker delta, I'll get 0 because it's constant for any given value of mu. On the very last term, the only non-zero term occurs when sigma is equal to 0. And so the divergence of the time vector field ends up being gamma mu mu 0. And that has a special formula that it's possible to show, is the partial derivative of the determinant of the metric with respect to the time vector field divided by twice the determinant of the metric. So let's look at the divergence of the time vector field in the flat space Friedmann-Robertson-Walker cosmology. In this cosmology, the metric has the form ds squared equals minus dt squared plus f squared of t times the quantity dx squared plus dy squared plus dz squared. In this case, dx squared plus dy squared plus dz squared is exactly the metric in three-dimensional Euclidean space. And so that's thought of as being the metric on a flat space. Euclidean space is flat. The thing that's unique here in the Friedmann-Robertson-Walker cosmology is that we're multiplying that flat space metric by an expanding factor f squared of t. The bigger f of t gets, the more it will stretch distances between points in space. It follows then that the determinant of the Friedmann-Robertson-Walker metric is minus f to the sixth. And you get that because you take the -1 from the first coordinate, and then you multiply it by f squared, and then you multiply that by f squared, and one more time you multiply that by f squared, taking care of the x, y, and z components in the metric. And so you get negative f to the sixth. That means that the divergence, calculating the derivative here with respect to time, the time coordinate, and we're using here Newton's notation for the derivative of an object with respect to time. Newton used a dot to describe derivatives with respect to time. And so if we're taking the derivative of negative f to the sixth, we'll need to use the chain rule and the power rule for derivatives. The power rule says bring that 6th power down and subtract 1 from the exponent, so that's how you get the -6 f to the power of 5. But the chain rule says you have to multiply by the derivative of the function on the inside, so you have to multiply by f dot being the derivative of f with respect to t. We're dividing by twice g, so we get -2 f to the 6th in the denominator. All of this reduces to 3f dot divided by f. By the way, if we were not using the flat space cross-section Friedmann-Robertson-Walker cosmology, but any other version of the FRW metric with curvature either positive or negative, the divergence of the time vector field would give you this exact same formula, 3f dot divided by f. For the flat space Friedmann-Robertson-Walker cosmology, f of t ends up being a constant times t to the power of 2/3. And if we then plug that into the formula for the divergence of the time vector field, we just get 2 divided by t. Taking the limit as t goes to 0 from the right, you can see that the divergence of the time vector field goes to plus infinity at the time of the Big Bang, t equals 0. There's something called the Hawking singularity theorem. It says, if gravity attracts on average, and space is currently expanding, then there exist time-incomplete curves backwards in time. The cosmological argument for the existence of God goes like this. Everything that has a beginning has a cause. The universe has a beginning, so the universe has a cause. What is it? Well, since all matter, energy, momentum, space, and time are part of the universe. The cause for this universe must be something external to those things. That means the cause of the universe must be external to all of the physics that we know. Quantum fluctuations, which some people have tried to use to explain the emergence of the universe from a vacuum, from nothing, these are just unscientific imaginings. You might as well call that cause for the universe God. What does the Bible say? In Genesis 1:1, it says, "In the beginning, God created the heavens and the earth." In John chapter 1, verses 1 through 3, we read, "In the beginning was the Word, and the Word was with God, and the Word was God. He was in the beginning with God. All things came into being through him, and apart from him, nothing came into being that has come into being." The stand is taken that God is the cause for the universe, and in the Gospel of John, it is Jesus that is the cause for the universe. So what happened before the Big Bang? The answer is nothing. Nothing happened before the Big Bang because time didn't even exist before the Big Bang, at least the time that is associated with our universe. It is possible that there are other notions of time outside of our universe. However, we are constrained to do the physics within our universe, and it's a simple fact that our universe didn't exist before the Big Bang. Thank you for watching this episode of the Cosmology and Jesus podcast. If you enjoyed this content, please give it a thumbs up, subscribe, and if you would like, make a donation. The link is in the description below.